Yeah.
Oh, now we're on. Are you ready? So,
That's insane. No.
water movement through plants. The other day we spoke about xylem, and we know that it's dead and hollow. And in the woody tissue of the stem. So we know it's dead and hollow, and it's called the xylem vessel. The xylem vessel. And we know that it moves water and ions up only. And we know that it's a passive process. Yes?
I just tell my mother I'm not going
Right.
to speak to you.
So the things we're going to talk about today are... Yes. 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 Right. So we're going to talk first about root pressure. So this occurs in the roots, and the root looks like this in cross section. Okay.
Why is everyone so weird today?
What's wrong?
Not being weird. Okay.
Right, xylem is in the middle. Around the vascular bundle in the root, there is a Casparian strip. So we'll consider that in just a second. So step number one. Step number one, we have the active transport of ions into the root. That makes inside the root hypertonic. Being hypertonic, it attracts water through the process of osmosis. Now we know in osmosis water moves from hypo to hyper, and because inside the root is now hypertonic, we know that water is going to enter the root. 3. Water enters the root. The big thing is the Casparian strip. So we know that we've got a Casparian strip. The Casparian strip allows water into the vascular bundle, but not out again. Right? Allows water in, but not out. So if water keeps going in, it's going to build up in pressure. And there's only one way to go, up. Water pressure makes the water go up. Sorry?
Adding my French teacher on Snapchat. Yeah, I saw that.
Adding my French teacher.
She added her French teacher. See.
So, had to borrow a whiteboard marker because mine's been removed. Okay, so that's root pressure. Okay, any questions? No? You can, if IMA is online, you can chat to her in the classroom, and she's at home watching.
She said she was going to join, but she couldn't find it. No,
It's just on my channel.
She put it on her story.
She joined.
There's a photo of him.
Right, so.
She definitely joined.
So here we go. Then we've got the next one is called capillary action. Capillary action. And in capillary action, this is moving up the stem. Now in the stem, in cross section, if here is the stem, so cut through the stem, we have our vascular bundles on the outside, the dicotyledons. Okay. There is a layer in the stem that separates the xylem and phloem. There's a layer in there that runs through, right, and that's called the cambium. The phloem is on the outside, and on the inside what we call the pith, is the xylem. Okay, so the cambium is the regenerative layer. Because the xylem is dead, the cambium regenerates live tissue. This is why we say if you were to ring bark a tree, what you're going to be doing is removing the cambium layer, which is that layer there, and that's the layer where there's active growth of new phloem tissue. And then as the phloem dies, it becomes xylem. Okay? Right, so it's going through the stem, and we're still going through the xylem. Okay, and there are two forces that we need to talk about. There is cohesion and adhesion. Now, water likes to stick together. So cohesion is between water molecules. I'll explain to you why that is in a minute. And adhesion is between water and the xylem vessel. The other day we spoke about what is inside the xylem vessel walls to keep them strong.
Lignin.
Lignin, well done. Lignin, because water likes to stick together, it pulls inwards. And so our xylem vessels have got lignin in the walls to provide more structural support so they don't collapse. Because they can collapse and you can get air bubbles in them that stop the movement of water. So it's really important they stay open. Now, chemists of the world, they do exist, I believe. Right. In water molecules, O, H, and H, the way that the bonding works in a water molecule, the oxygen attracts the electrons a lot more than the hydrogen. So we get what's called a delta positive, a slight positive charge on the hydrogens. And on the oxygens of other molecules, there is a slight negative charge. And so there's a little attraction there. And that's what is the cohesive force. They're just hydrogen bonds. Okay? All good? So the cohesion makes the water molecules stick together. Adhesion is when, remember in year 7, you had a test tube or a measuring cylinder. Yep. And then you had the water. You used to measure the meniscus, yes? The meniscus is because the water molecule likes to climb up the outside of, or the should be the inside of the tube.
Where do you measure?
Sorry?
Where do you measure?
Well, if you're measuring the water inside a measuring cylinder, you measure at the bottom there. But at the top, you get the little dip in it because water likes to walk up the insides of tubes. Right? And the rule for this is the smaller the diameter, that means internal diameter,
Lumen.
the higher the capillary action. And given that the xylem vessels are really, really small in diameter, water can travel a long way up the xylem vessels. And again, that's a passive process. It's just relying upon the properties of water. You don't need to apply any energy. All right? All good there? Then we've got one more thing to consider. Can I rub that off for you? No questions?
I know what you're talking about.
Marcus, any questions? Now we need to know, next week we're going to talk about the specific structure of a leaf. All right, so I drew it in very loose terms at the moment because we'll go into it in more detail next week. Okay? So this is in cross section. So here is the upper epidermis.
Is this a transpiration?
This is transpiration. I'll put the title up there for you. This is transpiration. Transpiration is the movement of water out of a leaf. So now we're talking about the structure of a leaf. So we have the upper epidermis and we have the lower epidermis. Okay, and the thing that we need to know about here, we do have other cells in there. We have the palisade mesophyll cells. We'll go through that next week. We have, though, the vascular bundle. And in the vascular bundle, because we've got xylem and phloem, xylem is at the top and phloem is at the bottom. Okay? Then we also have some other cells that keep it in place and also supply air spaces. So there's an air space. Here, this hole or pore is called the stomata. Well, stoma is singular, stomata is plural. But these two cells on either side are called guard cells because they guard the entrance. So we also have guard cells there. Okay? So in transpiration, this is what happens. We know that the water coming up the xylem, water travels in the xylem as a liquid. Okay. The water absorbs heat to become a liquid. And so if we were to write that now, we would over here, we would write H2O liquid becomes H2O gas, or what we call water vapor. And the way that we make that phase transition is through heat. Yes, Neve?
Is that saying you're not supposed to say gas then?
So you are right. My mistake. Sorry, Neve. To become a gas. Trying to go too quickly. Okay? So it absorbs the heat to become a gas. So here it absorbs the heat. Where does the heat come from? The sun, or from the leaf itself, or the environment? Okay, part of your course is to understand the adaptations that plants have to heat and a dry environment. And we'll do that next week. Okay? So now we've got H2O as a liquid, and it turns into,
In the air spaces.
goes out of turns into a gas in the air spaces, and then from the air space, it exits the stomata. Well, good, and that's transpiration. Transpiration is the movement of water vapor from inside the leaf into the environment. Okay. And next week we'll talk about a type of plant called a xerophyte. Xerophytes have adaptations to the loss of water in a dry environment. Okay? The good thing is it's not only in your course in year 11, but it's also in your course in year 12, xerophytes. Okay? Any questions? I know you're quite happy to go home today. It's been a warm day. All right, we'll finish it there. And next week we'll continue with our investigation of leaves and plant adaptations. All good?